Good day, Prof. Today we'll be going through our machine learning project presentation. It will be presented by me, Jacob Lawson, Samuel Lee, and Felicia Goh. So a brief introduction and problem definition. Our Kaggle competition was about the plant seedling classification, and it was hosted by the Aarhus University Signal Processing Group and the University of Southern Denmark. The dataset contains species of 960 unique plants belonging to 12 species at several growth stages. And the goal was to develop a machine learning model that can perform probability estimates on how likely a specified input plant is to a certain species of plant. A brief description of our dataset. So the 12 species previously mentioned are here, as well as their percentages in the entire dataset. So before we decided on which model to use, we had to identify whether we wanted to use object detection or image classification. So both object detection and image classification can do the job. However, image classification had limited use cases, while object detection had far more possible utilization. Example, farmers could use cameras that fed image frames back to the object detection models for multiple plant identification, not only one plant. And then it can aid the overall farming process. Hence, we use object detection. So, a brief introduction of the metrics we use to decide the model that we finally decided. So, IOU, intersection over union, which measures the overlap between bounding boxes, ground truth, and the prediction bounding box. Mean average precision, which is the average precision of the model across the different classes, as well as FPS, which is the number of frames per second that the model can evaluate and make predictions. So models considered: the single shot detector. This was released by Waylay in 2016, and it scored 74% mean average precision at 59 frames per second on benchmarking datasets such as Pascal VOC and COCO. So for its base networks, it used networks such as VGG16 and ResNet, whose job is to draw bounding boxes around the object. The SSD overlays grids or anchors around the image, and the network creates a set of bounding boxes at the center of these anchors. The fragments of pictures defined by the bounding boxes are then checked for the objects, and the non-maximal suppression eliminates all the boxes except for the one that overlaps the most with the ground truth bounding box. Moreover, it had additional convolution layers that are added to the end of the base network that decrease in size progressively to predict the predict the objects at different sizes and scales. And another model that we considered was the You Only Look Once model, the YOLO. Specifically the YOLO V4 model. It had around 76% mean average precision on the benchmarking datasets and could achieve over 130 FPS, which is drastically higher inference speed compared to the SSD. So how it works is that the network splits the input image into S by S cells. The center of the ground truth box cells in the cell, and that cell is in charge of detecting the instance of the object. It also supports the prediction across different scales, playing around with the different grid cells to detect smaller objects, as seen in the pictures below. In conclusion, we selected the YOLO V4. This was an easy decision for us because it had superior speeds and comparable inference accuracies compared to the SSD. Moreover, its recent popularity allows for more resources online. So now I'll be passing the time to Felicia, who will be going through Phase 0 and Phase 1 of our methodology.
For basic preparation, we did a few things. Firstly, for augmentation, we rotated the image by 90 degrees, 180 degrees, or 270 degrees, each with a probability of 0.5. We also flipped the image with a probability of 0.8 each, skew corner, skew tilt with a probability of 0.5 each, grayscale, and random brightness. Next, we split the training and testing images and renamed the images for convenience. Then, we convert the image labels to CSV to use as labels for TensorFlow, and convert the CSV to darknet to use as labels for darknet. After a slight augmentation, this table shows the training dataset that we used for our model. The last three plant classifications as shown in the table are slightly underrepresented with only 4 to 5.5% of the entire dataset. For the darknet YOLO v4, we first configured our GPU environment for YOLO v4 on Google Colab and installed the training environment. We set our batch size to 64, subdivision to explore 12, max batches to 200,000 times the number of classes, and we trained the model until there was not much fluctuation in the accuracy score. For TensorFlow, we converted our model from darknet to TensorFlow and ran our detect file to detect the images based on our model and saved the outputs as a CSV file. Now I'll pass on to
Okay,
Samuel.
so now we'll talk about our phase one model implementation. And basically this phase is used to just test out the different models and familiarize ourselves with the flow of how to train the models. So we use the list of the test images and then we feed it through a basic model like SSD MobileNet v2. And we also tried another one which is YOLO v4, which is an object detection model, and we got the class out. We also got things like the accuracy score and the bounding boxes. While I know this is not really like it doesn't have to be object detection, but I think we use these object detection models because we want to possibly branch out these projects further and be able to further improve things and be more practical, like being able to use it for multiple object detection or portability. So for our augmentation images, we use 27,000 for both models, and you can see that there's a pretty big disparity in the accuracy scores. Obviously, because the mobile net is a lot more simpler compared to the YOLO V4. That's why there's a difference. One is 51% and the other one is 83%. So after this like experimental phase, we kind of looked at what are the roadblocks that we face or what are the complications that we face. And we asked why are our results so far from the top leaderboards. So is it because of the parameter tuning, like the batch size, or is it because the images are too similar to each other? So like you can see in the pictures below, we have black grass and common wheat and loose silky band. And you can see black grass and common wheat is actually really similar. And sometimes also maybe, sorry, black grass and loose silky band is really similar. And also sometimes common wheat. So is this something that our model is unable to differentiate? Possibly. And also augmented images, like things like should we be using grayscale? Should we be using the augmentation of like saturation, zoom, that kind of thing? What if I zoom into just the ground? What if I crop into just the ground and rotation? So what augmentation should we use? And also, is YOLO V4 good enough? And are there any enhancements that we can do? So this was our answer for phase two. So in phase two, we look at some possible enhancements. Obviously, we played around with the parameters, and we also added this time test augmentation or a variation of it. So we did the same thing. We used a series of test images, but the thing that we did differently this time is to augment these test images. So like you can see, we didn't just use three, we used more. But in this example, I show like tree where we can do grayscale, we can darken, we can brighten, and then it kind of gives our model like a second chance or second look, or I mean more than two times, obviously more chances and more looks to like look at this image and decide what it really think it is. So we run all the images through the model and then we kind of get like a list back, like maybe Charlock, and then breakfast. And then we'll just kind of use the majority. I know that time test augmentation uses like mean of the accuracy scores and all that. But for this one, since we implemented it ourselves, we just decided to go with this particular version first. And we also increased the augmentation images to 54,000 and in this phase two with time test augmentation. and we got a better accuracy score of 94%. I think that this is not all because of the time test augmentation. Obviously, it's also because of our augmentation images, but I do believe that the time test augmentation did help in our accuracy score. So giving the model like a second, third look and being able to choose the best majority. So we looked at our roadblocks again, and I think we tried most of it in phase two already. So the one thing that we didn't try is how do we solve this like image similarity issue? We look back at the discussion boards in Kaggle and we realize, okay, other people are kind of facing this issue also. Like these images are just way too similar to each other. So what can we do about this? And this is our answer for phase three. So we did a specialized model training. As you can see, the first part is still the same as phase two, but we train a three class YOLO v4. So these three classes are blackgrass, loose silky band, and common weed. So every time this first model predicts one of these three classes, we will send these images over to our second model, and then we'll decide whether it is really blackgrass, common weed, or loose silky band. And if not, it will just do the normal flow. And with that, with the same amount of augmentation images and these two models, we managed to get an accuracy score of 97%. And which is kind of an improvement. We did try to do other further experimentations with maybe like YOLO V5X, but it didn't really increase our accuracy score. As you can see, the augmentation images we use are lesser also because this YOLO V5X really takes up a lot of RAM. So this is just a summary of our pipeline, which I kind of explained most of it previously. And so this is our conclusion and some possible improvements. Obviously, we hope that the second model will really boost our accuracy up, maybe to like 98, 99%, because our models were also trained to like 99%, but perhaps it was kind of like overfitted or just a very small, variant. So, we also had some questions as to like whether the grayscale images really helped because for some of these maybe the color really does matter, the slight shade of green did matter, but it seemed that when we added some grayscale images in our augmentation, it did help to improve the performance, maybe to make our model more versatile. So some possible enhancements that we would possibly like to do is that if we really wanted to focus just purely on accuracy, we could use some of like not object detection but more like classification based to integrate it maybe into our second model to boost our results. Things like ResNet 50 and yeah, like I said just now, we also attempted variants like YOLO V5X, but the RAM just took up a lot of it just took out a lot of RAM. So overall, we got pretty decent results, which is the top 27%, as you can see here. So we got this 97%, which is our final result, and leaving us at around 230 or 229. I do understand that we sacrifice a bit of our accuracy when we use like the YOLO object detection models instead of just the purely classification models. But I do believe that it is kind of worth it because um, it's much more practical in a sense where you can do multiple object detection next time. Maybe if we made it portable, farmers could use it for different scenarios. If we possibly change the target object, we could do these object detections for different things. And YOLO V4 is a pretty fast model, close to real time, and V5 is even faster. So, there's so much room to like expand out instead of just purely making this a classification project. So that's why we decided to go with this. And yeah, so this is most of it. So I think that overall we are satisfied with our results and we really learned a lot from this whole project. Thank you.